In our previous video, we took a look at how to use the Runge-Kutta method to be able to approximate at least one iteration to see how good of an approximation we can get for a first-order differential equation. And now what I'm going to do is I'm going to show you how to utilize Excel to be able to do this. So what I did was I went through and I took the liberty of setting up all the columns for each of the different constants k, k1, k2, k3, k4, and these are the formulas. All right, so if you're using Excel to do this, then this is how you're going to have to set it up to be able to get each of the different k's. You certainly don't want to program it all in one cell. You could, but I certainly wouldn't suggest that. And then this is going to be our next y value. All right, here's our differential. Y prime equals 4x minus 2y. Y0 is 2, and we're looking for y at 0.5 using the step size 0.1. All right, so now you might remember that the improved Euler's method I believe that we found that with the improved Euler method, we got to 0.78% error. So let's see if the Runge-Kutta method gives us any improvement on that, or maybe just the improved Euler method might be the best way to go. So we know that when x is 0, the initial condition is that y is 2. We want to get to 0.5. And so that means we're going to need 5 iterations. So let's get programming. All right, so we're going to say that this is going to be equal to 0.1 times our function at xn, yn. So that's 4 times xn, and I forgot the equal sign here. So 4 times xn minus 2 times yn. All right? And you might remember by hand when we did this, we got negative 0.4. So we get negative 0.4, so that's a good sign. Remember, we got negative 0.34 for K2, so let's see if we can get that. So that's going to be equal to 0.1 times the quantity of 4 times the quantity of current x, which is 0, plus 0.5 times 0.1, minus 2 times the current y, plus 0.5 times k1, which in this case is right here. I need to make sure we close all the parentheses. Now remember, we got negative 0.34, and we get negative 0.34 again. For K3, I believe we got negative 0.346. So let's see if that happens. So we have equals 0.1 times the quantity of xn plus 0.5 times 0.1. I'm sorry, 4 times this quantity. So 4 times this minus 2 times yn plus 0.5 times K2, which is this quantity. So let's see if we get negative 0.346, and we do. All right. And the last one, we got negative 0.2908, I think, or 2906 or something like that, negative. So let's see if we can get that. So equals 0.1 times the function 4 times current x plus 0.1, which is our h, minus 2 times current y, plus K3, which is stored in this cell right here. Now I'm going to close my parenthesis, close this parenthesis, and we got negative 0.2908, all right, which was the correct value. Finally, we can figure out what the next y value is. And you might recall that we got 1.6562 or something like that. So 1.6562 I think we got. So that's going to be equal to the current y plus 1/6 times K1, which is stored in D2, plus 2 times K2, plus 2 times K3, plus K4. All right, and hopefully we end up with that 1.6562. 1.6562. So either we got extremely lucky or it worked. and based on probability, it's most likely that it worked. Now remember, the next y is going to be this value, so we're just going to say that this cell is now going to be equal to whatever's stored here. And just like we've done in the previous videos, what we're going to do is now we're going to drag. All right, so we're going to drag this, and initially it's not going to look good. All right, drag this, drag this. So now we're getting different k values each time, different k value, and now we're going to get the next yn. All right, and hopefully this is the one that we really want. All right, and let's see how good of an approximation it is. Okay, so this is our answer right here, our approximation. And just like in the previous videos, let's see how good we made it with this. All right, so I'm going to insert a couple columns. All right, so this is going to be our y actual, and this is going to be our error. And remember our improved Euler method. All right, remember improved Euler gave us 0.78%. So that was pretty good with improved Euler. So remember our y actual is 2 times x, which in this case is stored right here, minus 1 plus 3 divided by exp of whatever's stored. And that should be 2, which it is. Let's drag this. Let's see. Oh, it was 2 times this, excuse me. Alright, there we go. Then we have to drag this. There we go, that looks a lot better. Right? Let's see what the error is. Alright, so this would be equal to the absolute value of the approximate minus the actual. So it's going to be equal to approximate minus actual divided by actual. All right, now the first one's going to be 0. No surprise there. We drag this. Oh boy, we're getting some... Oh, I think it just drug error by accident. So let's just drag this. We're getting some really small values for this. All right, so notice that if I were to convert this into a percentage, so I'm going to format our cells, percentage, and let's just go out to maybe, let's not be ridiculous, but let's say 7 decimal places. All right. Notice that the Runge-Kutta method gives us 0.0015758. So that's actually much, much smaller than the improved Euler method. All right, so this Runge-Kutta method is extremely powerful, and notice that the step sizes are still relatively large. So if we wanted to, we could really increase those step sizes or decrease those and get an even better approximation. All right, so from a simplicity programming standpoint, it's probably best to utilize this Runge-Kutta 4-step method. All right. The improved Euler method is just a forward difference, and it works really nicely, but it does take a number of iterations. And then the regular Euler method again takes even more iterations. So make sure that you can utilize Excel to be able to help you to solve all these different ways. All right. It all comes down to runtime, because as you notice, you have to do basically 4 recursive steps to be able to get to the answer. So even though this gives us a much better accuracy, unfortunately what we have to deal with is a lot more runtime on our computer. And so that's the trade-off with this, is how precise do you want to get versus how many iterations do you want your computer to run. And we know that memory is pretty cheap nowadays, but in the older days, when I was doing this using a calculator, memory was a little bit more expensive. And so maybe something like this might not have been as good for us to run on a computer because of how many steps were necessary. All right, so that's just why we have all these different algorithms, as opposed to just using the quote-unquote best one by looking at error. Sometimes the best one might be the most efficient runtime, and that's where we might have to go back to those Euler methods.